to compute transport through this structure when there is no bias, so it's not a standard situation. But what I want to compute is the current when, for example, the coupling of these levels to the left and to the right, or the position of the levels themselves is time dependent. I want to consider a fully time dependent problem and compute what is the resulting current. Now, if you remember the initial step of yesterday's calculation, there was no reference to the fact that we are dealing with a time-independent problem. So we could use, so from now on, EH, bar, etc. are set equal to 1, but we can use a formula that is reminiscent to what we had yesterday. So I alpha is equal to twice the real part of sum over I and k v alpha I t, and then I had the g lesser I k alpha I t t. So this is my current. Exactly the same formula I had yesterday. The only difference as compared to yesterday is that I'm already making from the beginning the simplification of taking the tunneling matrix elements to be independent on the quantum number of the leads, the momentum quotation marks k. This is a major simplification. I'm not saying you cannot do the calculation again, putting back the dependence on k of the matrix elements. It's just going to be more cumbersome and complicated, but the final result is going to be the same. So let me do this simplification and therefore write this as twice real part of sum over I v alpha I of t, and then sum over k g lesser k alpha I dt, and this is nothing but, we call it g lesser alpha I dt. Okay, so now our goal is to compute this g lesser alpha I dt. We are going to proceed along the same steps as yesterday. So you understand that when you look at this green function, you're going to have exactly the same story as we had yesterday. The general structure of the perturbation theory for this green function, so g k alpha I tt prime, contour ordered, is going to be this one, provided there is no interaction within the leads. So everything that I've done for a time-independent problem is valid also for the time-dependent problem. If you think for a second, you immediately realize it. Now, the only complication is that when I translate this formula, so I take the lesser component of this, now I have to deal not with convolutions of functions that depend on time differences, but with functions that depend on both time arguments. And that is the essential complication of this problem. So essentially what we discover is that this guy, tt, is equal to, tt prime is going to be equal to sum over j integral dt1. So this is the integration of this vertex here. And then you're going to have sum over k g lesser k alpha tt1, then vj alpha t1 star, and then g advanced ji t1 t prime, and then you're going to have plus sum over k G retarded K alpha T T1, then V alpha T1 J star, and then Gij lesser T1 T prime. Okay? All right, so the summation of their K here that I didn't have yesterday comes because here I'm taking this summation. So I redefined my green function with the summation over K explicitly. So now you see the major simplification comes because the summation over K involves only green functions in the leads, these two guys. And this is something easy to compute in principle. Let us start with G lesser. Alpha is still left or right. Yes, absolutely. And I and J are the indices of the levels in the quantum dot. Right, so G lesser. Now, G lesser, I told you yesterday what it is. G lesser of omega is equal to 2 pi I delta of omega minus epsilon k f of omega. This is what we wrote yesterday. So clearly, we have that G lesser k alpha t minus t prime, because it depends on the time difference, is going to be equal to I f alpha of epsilon k times e to the minus I epsilon k t minus t prime. This is what you get if you take the Fourier transform of this, right? And now we're interested in taking the sum over k of this. Now, of course, we will pass from the sum to an integral. Of course, in general, when you pass from the sum to the integral, you have to worry about an energy-dependent density of states that, as I did yesterday, I'm going to take out of the integral and assume that it's constant. You can keep it in if you want. It's not going to matter at the end. All the results are okay. So, therefore, I will have that this is I times density of states times the integral in d epsilon of f of epsilon e to the minus I epsilon t minus t prime. Well, this is I times density of states times f of t minus t prime, where f of t minus t prime is the Fourier transform of the Fermi function. Now, all of you should be screaming and, tearing your clothes when you see this. Because do you think the Fourier transform of a Fermi function exists? I mean, it's a highly singular object. Let me put it this way, because the Fermi function goes to 1 at minus infinity, and therefore this integral is strictly speaking not convergent. So you can make it convergent, for example, by putting here an exponential regularization, right? You decided that this is e to the minus eta t minus t prime, and then everything is going to be cool and fine. Sorry? We're doing any temperature, it doesn't matter. At any temperature, this Fourier transform does not exist. I mean, the integral does not exist in a standard way, right? So you have to regularize it. So I am assuming that I'm regularizing it in some way, and I'm going to forget that I'm regularizing it. So through the calculation, There is a regularization, but at the end of the day, you will see that it doesn't really matter which regularization you use. The final result is okay. But we understand that we have to do it one way or another. I don't understand your... Yeah, I mean, the problem is that it's like taking the Fourier transform roughly if you forget about the smoothness or not of a theta function. So it's a pole in which you have to take the, the limit to 0 of an imaginary part. It's a singular object. So what I'm saying is regularize it some way. Even at finite temperature, you are going to have the same problem. So you have to regularize it. But at the end of the day, the statement is, no matter what the regularization you choose, you could put here a Gaussian, for example. It's a regularization. Fine. No matter what the regularization you choose, you will get the same result. And you will see at the end why. So now, let us move on. Now here it's even more intricate in a sense, t minus t prime, because g retarded t minus t prime is e to the minus I theta t minus t prime e to the minus I epsilon k t minus t prime, right? Yes?
Does this regularization depends on the density of states?
Oh no, in which sense?
We taken it as a constant.
Yeah, so I mean, okay, you're absolutely, this is a very good point. If you are not a lazy person like me that took here a density of states as a constant and put the limits of integration to minus infinity and plus infinity, then you work in a finite band, right, with finite boundaries, then you don't need to worry about the regularization, right? So, but at the end of the day, then you will need to worry about the fact that your result is independent your final result is independent on the bandwidth, which is going to be correct provided that the temperature is much smaller than the bandwidth, right? So at the end of the day, yeah, you're right. If you put the bandwidth there and you don't take a constant density of states, you don't need the regularization. Absolutely. Okay, so now I have to compute the right. I have to compute sum over k of g retarded k alpha t minus t prime. Well, you see that this is minus I theta of t minus t prime times the density of states times integral d epsilon k e to the minus I epsilon k t minus t prime. And this is minus I times the density of states times 2 pi times theta of t minus t prime times delta of t minus t prime. Again, using my weird desire of simplifying things, I made them a bit more complicated, but not too much. Because, look, what is the product of a theta function times a delta function? What can it be? Well, the product of a theta function times a delta function is, of course, half of a delta function. Of course. It depends on how you regularize it, right? But, it's sitting there at the center of the theta function. So if you regularize it in a symmetric way, you will get the factor 1/2. Okay? Again, if you want to be precise mathematically, put back the boundaries in this integral, do all the integration. you will get the same result. So it's okay. All right, so now that we have that is the Fourier transform of a Fermi function, and this is the the delta function, now we can take these two formulas, you see this one and that one, and plug them back in that expression, and take the integral over dt1 explicitly. So what we're going to get is that our G lesser K I alpha dt prime is equal to sum over J integral dt1 of 2 pi density of states I f of t minus t1, and then I will have bj alpha t1 star g advanced ji t1 t prime, and then plus, or actually minus, the minus comes because I have because of what? Wait a second. Because of this minus sign here. So it's going to be minus sum over j, and then, wait a second, here there was a factor of 2 pi that I forgot. So this goes with that. And then you will have pi density of states I bj alpha t1 star g lesser ji t1 t prime. Okay, so now we look at this expression and we plug it back into the expression for the current. That's, well, is it going to be there or there? Who knows? What? I should go up the other direction? You have more experience. Yeah, right. So now we have to go back to the expression of the current. This one. Now you see what is the expression of the current. There is a 2 real part sum over I. So let me rewrite it here so that I can go down. 2 real part sum over I vi alpha t, and then g lesser g lesser alpha I t t. Right. So now, correct? Yes. Yeah, sorry? It didn't. Which expectation value? I mean, this one? No, it's not an expectation value. I don't understand really the question. So what do you think is an expectation value? Where is it?
That equation you have angular brackets around IR.
Here, this is the current, the average current flowing out of the lead alpha.
Brackets.
Sorry? What is the meaning? It's the same as usual. So I pick the initial state, I time evolve it forward with my time evolution operators, and my initial state then is something I don't care about, and I send it to minus infinity. Same story that we have done in the second lecture that I think was 2 days ago, right? So it's always the same. The reasoning is always the same. So it's an expectation value with respect to the initial state. But the initial state at the end is not going to appear because I don't care about it. I'm interested in the stationary state. You can ask me, what the hell of a stationary state are you interested in here, that it's a time-dependent problem? Well, the thing is that I'm going to assume that the parameters are varying on a cycle, right? It's as if you're putting, it's like when you put a voltage bias that is oscillating, right? AC bias. So it's time dependent, correct. But in the stationary state, you have an oscillating current that oscillates with the same frequency. And what I will be interested in is what is the average oscillating current. And that is not going to depend on the initial state. That's my statement. Right, so, okay. So now what I want to do is exploit this structure. So you see, okay, so you see how things work. There is a VI alpha, and then this function here. This function here is this one. And then, well, there is a VI alpha t, and then, oops, yeah, there is a VI alpha t, then a Vj alpha t1, and this t prime is going to be equal to t at the end of the day because I'm interested in the green function at equal times. So I'm going to have Vj alpha t1, Gij t1 t, and then Vi alpha t. So a clever way to rewrite this in a formally expressive way, something that has a physical meaning, is the following. Let me introduce the analog of the T matrix that I introduced yesterday. That was a transmission matrix for scattering. This one is a formal object for the moment. But let me introduce it anyway. So I introduced the retarded, advanced, greater, or lesser T matrix, alpha, beta, that depends on two times in general, as 2 pi density of states sum over I and j Vi alpha t star g retarded, advanced, lesser, greater, or lesser I j t t prime, and then V beta j t prime. So you see, these are the type of structures that will appear the moment you put this function in here and take equal times. Now this is what will happen. You always have a density of states, you always have a pi, you always have what is needed. So at the end of the day, therefore, the physics, what is going on here? So at the end of the day, the formula itself is the formula itself for the current is telling you, you have to write me in this form. And, well, the formula is always right. So the way I have to write the formula is this. F of t minus t1, t advanced alpha alpha, t1 t, and then minus, so let's put this under parenthesis, and then minus I over 2 t lesser alpha alpha tt. If you look at it, it's not very much different than the expression for the current, the general expression for the current that we got yesterday. Also yesterday we had an isolated G lesser, and then we had a T advanced that when you take the real part gets subtracted with T retarded. So it's the same kind of structure. What is the problem of this? Well, this is as far as you can go for an interacting system, right? So if you have an interacting system, you stop here. I have a paper with a student many years ago that manages to get a Brouwer type formula for this, but it's too complicated, and I don't think it's pedagogically useful to tell you the story at the moment. So you have to know that you can write something like a pumping formula for an interacting system, so the analog of what I wrote yesterday, but I'm not going to tell you how today. What I want to do, because it's pedagogically useful in my opinion, is to tell you the story of the non-interacting system. And the story of the non-interacting system worked out using Keldysh is something that I have done with the late Avi Schiller in 2007. So you can find, I have only one paper with Avi, so you can find it online, and it's in, what I'm going to tell you is essentially sitting in the appendix of that paper. Now, the story is the following. Step number one is this. You don't want to, if the system is non-interacting, you don't want to have this T lesser here, because, well, we know that we can get rid of it. So, in particular, T lesser alpha alpha TT is equal to 2 pi density of states sum over I and j B alpha I T star G lesser ij tt, and then, well, V alpha j t. Now I look at this and say, aha, wait a second, I know how to write this. Because I know that I can use the Keldysh equation I told you. G lesser equal to G retarded times sigma lesser times G advanced. Now, I wrote it in terms of, as products of Fourier transform, but it's true always. It's true also for convolutions, complicated convolutions like this ones. So here, let me write G lesser ij tt prime in general is equal to sum over p and q integral dt1 dt2. And then I'm going to have G retarded IP TT1 sigma lesser T1 T2, and then you will have PQ, and then G advanced Q J T T2 T prime. And what is sigma lesser? If I have, yes, right? It's, yeah, it is always valid. I mean, it's not true. I explained to one of you, I don't remember whom, after the lecture when I explained this, that it's not always valid. The statement is, so when you write this expression, what you are implying is that your stationary state does not depend on the occupation, does not depend explicitly for this this system on the occupation. Does not depend explicitly on G naught lesser. So the occupation of in the non-perturbed state is not entering explicitly in the expression for the stationary state. There are situations in which this is not true. And let me not enter this story, but for this particular case, it is correct. Right, so it is quite general. I mean, it's almost always, unless you're looking at a pathological situation, it is always, it's correct. Right, so what is the only self-energy insertion we have here? Well, it's a non-interacting system, so that's it. We know it. We have done the calculation yesterday. It's a non-interacting system. And this is equal to 2 pi density of states I sum over alpha via p alpha t f of t minus t prime v q alpha t prime star. Now, of course, it's not something that is automatic, right? Here, this is a lesser component, so you're going to get a g lesser k alpha t minus t1, t1 minus t2, summed over k, but you know, we already performed this sum a minute ago, and we're going to get the Fourier transform of the Fermi function, and then this has to be multiplied by these tunneling vertices on the left and on the right. So that's why you get this expression, okay? All right, so now we look at this and say, well, look, life is easy. I have V, G retarded, V. Sorry, V star, G retarded, V. And then again, V star, G advanced, V. Which means that I'm able to rewrite everything in terms of retarded and advanced T matrices. So in other words, I get that my current, I alpha, is I integral dt1 of f of t minus t1, t advanced alpha alpha tt minus, sorry, t1t, minus t retarded alpha alpha t t1 f of t1 minus t, and then you will have plus sum over beta. This is what comes from that t lesser. Sum over beta integral dt1 dt2 of t retarded alpha beta t t1. Then you will have f of t1 minus t2, and then you will have t advanced beta alpha t2 minus t. And does it look complicated enough? It does, right? Now, luckily, at this point, we can simplify just by using physical intuition. You don't need to think about mathematics. Now, this expression is written in terms of T matrices. I remember, I was just, my first year of postdoc. I looked at this expression and said, well, look, maybe I should use the same relation between the S matrix and the T matrix that exists for the standard scattering problem. So let me define, so in the standard scattering problem, the relation is this. S is equal to the identity minus ida times the transmission matrix. Now, here I'm dealing with time-dependent objects. Now, for a time-dependent object, what is the identity? I always think about these convolutions as products of matrices. I mean, that's in my head, right? So what is the identity? It's a delta function. What else? So let me define then S alpha beta t prime to be delta alpha beta delta t minus t prime minus I times what? Well, the scattering matrix is something that connects stuff that goes forward in time. So here I put the t retarded, t prime, alpha and beta. And then I want to know what is S dagger. So S dagger, alpha beta, t prime is equal to, wait a second, delta alpha beta, delta t minus t prime, plus I, And here, well, the complex conjugate of the retarded stuff is the advanced. So I will have T advanced alpha beta T prime. All right, so, and then you ask yourself a question. This construction makes sense. I mean, I can interpret this as an S matrix. What is the property of that the X matrix should satisfy? It's a unitary matrix, right? So if I want this to be a proper definition of an S matrix, it should be unitary. And therefore, I have to check that sum over gamma of integral dt1 S alpha gamma pt1 S dagger gamma beta t1 t prime is equal to delta alpha beta delta t minus t prime. Well, it turns out that it's correct. Intuition is always useful, right? This formula is correct. It's a consequence, actually, of the Dyson equations for the retarded and advanced green functions. So I'll leave it to you, to the brave of you, to prove it as an exercise. It's not hard. And if you don't, if you get stuck, look at the paper with Avishila, and you will find the solution there. But it's not complicated. Again, it's a consequence of Dyson equations and nothing else. So, bottom line, now we have an expression of the, now we can introduce these guys, and now we can express the current in terms of S matrices, which is useful, right? And that's what Landauer told us to do. So the current I alpha comes out to be integral dt1 dt2 of sum over beta S alpha beta tt1 f t1 minus t2 S dagger beta alpha t2 t minus, and now you have this weird thing that you have to keep, but it's due to all the weird things that we have done with with non-regularized or whatever singular objects before, but think about it as being regularized appropriately. So formally, you will see how this enters in the calculation in a second. Right, so we have a formula for the current that is in the same spirit as Landauer, right? It contains the distribution function written up in the time-dependent fashion, and then it contains my time-dependent S matrices. And now, well, this is the most general formula I can ever write for transport for time-dependent transport through a non-interacting region. Now the question is, what do I do with it? Well, so you can start, playing the game of what I call zoology. So you can choose some time dependence, and then you compute for your favorite model. What is the current? It's quite a lot of waste of time, but it depends on how much time you have. But in principle, you can do it. Or you can try to do something more clever. And this is what Pete Brower did. He said, okay, look, let me try to consider a situation in which I have a separation of time scales. Now, this is very common in physics. Tomorrow or today, or I will start today, I will finish tomorrow, we'll see how it goes. I will use the Keldysh technique to derive the Boltzmann equation for you. Now, the Boltzmann equation is a semi-classical approximation when you see it from the point of view of quantum many-body physics. And then you have to ask yourself, when can I use a semi-classical approximation? A semi-classical approximation can be used whenever you have separation of time scales and length scales. So, for example, you have a potential in your electron system that is varying on a scale that is much, much longer than the Fermi wavelength, right? If instead you have a lot of disorder, and the mean free path is comparable to the Fermi wavelength, you don't have semi-classics. You have localization, you have Anderson localization. What about times? Well, if you have your time parameters that are varied on a cycle or on whatever, with a time dependence that is very, very long as compared to the inverse of the Fermi energy, which is the typical time scale of evolution of a wave packet for a fermionic system, then, well, you can pretend that you can sort of be semi-classical. So here we want to do something similar. We want to take a sort of, it's not a semi-classical approximation, he called it adiabatic approximation. Well, why? It's not up to me to decide. But the story is the following. I'm assuming that I'm thinking physically in the following way. I have this resonant level. An electron comes in and stays here for a while, right? What is this while? Or how much time does it stay here? It stays here at time, let's say tau, that is of order of 1 over gamma, right? Because then it escapes, right? Because of the coupling to the leads. So if the variation of my parameters, Vt, gamma, epsilon, whatever, is very, very slow, so it has a time scale that is very, very long as compared to this one, then in practice, this electron here sees something like the instantaneous parameter or a slight variation from the instantaneous parameters. So you have a small parameter for your theory. So if this is much smaller than T naught, you have a small parameter that is tau over T naught. And when you have small parameters in physics, you're happy because you can make expansions, right? You never know whether they are perturbative, they are convergent, they are symptotic series. Nobody knows. But at least you can expand something and get a result that has some benchmark in something that you know. Right, so how do we do now the expansion here? Well, the thing is the following. If you look at these expressions, these are all convolutions. Convolutions of objects of these S matrices. Now, these S matrices, S of T prime, roughly, alpha, beta, are equal to delta, alpha, beta. Well, I wrote it there, right? And there is no need to rewrite it. Schematically, they are delta minus I, V, G, T, T prime, V. Vt, Vt prime. Now, it is clear that this function here is containing information about gamma, right? If you pass to, for example, if you pass in this function to what are known as Wigner coordinates, so instead of using t and t prime, you use t minus t prime and t plus t prime over 2, and this you call it tau, and this you call it big T. Well, you can expect that the dependence of this function of tau on tau is going to be controlled by 1 over gamma, and the dependence on t is going to be controlled by t naught. Why? Because, well, think about it. Look at the expression. Imagine that it was time independent. So this was minus I theta t minus t prime e to the minus I gamma t minus t prime e to the minus epsilon I epsilon t minus t prime. Now, you see where is the dependence on t minus t prime. Now imagine that you turn on a slow time dependence on gamma. What is the simplest approximation you can make? Well, you make this time dependent, right? You make the level and the gamma time dependent in the green function. It's a sort of, well, I don't know, isn't the same spirit, if you think about it, of the Thomas Fermi approximation, even though that is a completely different story, but the logic is the same. Okay, so all I wanted to say, therefore, is that this green function, you can expect it to depend, to have a fast time dependence on the difference and a slow time dependence on the average. And now we want to exploit this. How? We exploit it in the following way. In general, what we are dealing with, so what I'm going to teach you now is a very general technique that you can use for everything in field theory, even other calculations. And it's called a gradient expansion. I'm sure that you can use it also for classical StatMech. And people used it some way or another. Yeah, here I'm rewriting the green function in two other coordinates, tau and t. So the story is the following. You see that in that expression there, we are dealing with convolutions, with a bunch of generalized convolutions of stuff that does not depend on time differences. So in general, we are dealing with objects like this. Okay? This is the, mathematics. Yes?
Here you are using two types of variable, that's tau and are you saying that because of the scale separation I can look at, I can do Fourier transform of one variable?
Yeah, absolutely. You will see that I'm going to do that in a second. So, as is said, here I can introduce two variables, tau and t, as above, as I've done above. And because of what you just said, because of scale separation, I can take the Fourier transform with respect to tau. This has a name. It's called the Wigner transform. Wigner transform. So it's called the C omega t. It's just a Fourier transform with respect to tau. But now the problem is that if I take the Fourier transform with respect to tau of c, the Fourier transform of a convolution is not the product of Fourier transforms, because these functions are not dependent on type differences, and the convolution theorem is not valid. Luckily, you can generalize this expression to the following. This is equal to, and if you want the proof of this, you can find it in the book that I mentioned already a few times by Yaucho. So the Fourier transform of this, the Wigner transform of this is A of omega and t times an operator, differential operator G of omega t, and then B of omega and t, where G omega t is equal to the exponential of 1 over 2i, the derivative with respect to t acting on A, the derivative with respect to omega acting on B, minus the derivative with respect to omega acting on A, the derivative with respect to t acting on B. Okay, so what is the meaning of this? Of course, I mean, the meaning is that now you start expanding the exponential and taking the derivatives, right? So, I mean, the way you prove it is just by re-exponentiation. So you prove it term by term in an expansion, and then eventually you show that you can rewrite it in this exponential form. But the way you use it is just by taking the expansion explicitly. So in practice, if you expand this to the first order in the gradients, you will get the product of Wigner transforms, and then plus 1 over 2i, you will have dta d omega b minus d omega a dtb. And then you will have higher orders. Now, what is interesting is that whenever, right, so whenever I look at one of these products in which I have a derivative with respect to t and a derivative with respect to omega, now the derivative with respect to t will take down in the, so if I have a separation of scales, the derivative with respect to t will take down a factor 1 over t naught, right? While the derivative with respect to omega will take down a factor 1 over gamma. And therefore, in front of this guy, I will always have, roughly, a product 1 over t naught gamma times t naught, which is tau over t naught, which is my small parameter. Therefore, when you have a separation of scales, then the expansion in gradients is also the perturbative expansion with respect to this small parameter. Okay? So that's how you take a semi-classical approximation in this context. All right. Is it clear to everybody, or I lost all of you? And it's clear, hopefully. Okay. Right, now we know this, and we can do the expansion in gradients of that expression. It's not an easy cake. Yes? Yes. Well, this one disappeared. So as I mentioned, the T lesser was using the Keldysh equation. You see, this is the T lesser. Using the Keldysh equation, that is G lesser equal to G advanced sigma lesser G retarded sigma lesser G advanced, I was able to rewrite the T lesser as a T retarded F T advanced. So, sorry? There. No, but the T lesser is alpha, is TT, is not inside the integral sign. Here is sitting, so this first integral up there is this one. And then the T lesser has, is TT, and then I have these two extra integrals that come from this equation. There should be a bracket. Where? Ah, okay, you're right, here. Is it correct? Yeah, hopefully so. Okay, so we add the bracket to the stuff that is equal to 1. Okay, so we are almost done, and we will get soon to the physics. No. Shoot. Okay, so now you take that formula that I wrote up there. Oh, where is it? And you take the gradient expansion of it. So in practice, what you have to do is like taking contractions of terms pairwise and then expanding it in gradients. It's a bit of, it's a bit of algebra, but it's not complicated algebra. You just have to be patient and go step by step. At the end of the, yes? Why do I want to expand in gradients this S matrix? Well, because I told you, I know that I focus on the specific case in which I have a separation of scales. So I have a fast time scale, which is the time scale that the electron spends in the scattering region, and I have a slow time scale, which is the time scale with which I'm moving my parameters. And now I'm saying, well, look, in all these functions, the fast time scale is the difference, and the slow time scale is essentially the average. So if I do an expansion in gradients of this expression, it's going to be an expansion in the small parameter tau over T naught. Okay? So that's why I want to do this expansion. Because this is like, here we are in the kingdom of Homi Bhabha, and he was he liked aesthetics in art and in physics. So this is because of aesthetics, right? So this looks ugly, and when you write it in terms of S matrices, it looks much better. So I wanted to go from there to here because it's simpler. And you will see in a second that the simple is, the beautiful is also the good, and is also the correct. So you will see that you will get a nice result at the end. It's, but I was not guided by general principle, just by aesthetic principles, nothing else. Okay, so what I wanted to say. Okay, you do your expansion, I alpha. And, well, so you start expanding, and what you get is d omega over 2 pi. So I'm writing down the final result, okay? You have to do the calculation yourself, but you will get sum over beta S alpha beta omega t S beta alpha omega t dagger minus plus 1 over 2I dt S alpha beta omega t d omega S dagger beta alpha, and then d omega S alpha beta dt S dagger beta alpha minus 1, and then plus minus sum over beta. Let me write it in a different color. Sum over beta integral d omega over 4 pi I, and then minus d omega f dt S alpha beta S dagger beta alpha minus S alpha beta dt S dagger beta alpha. Okay, so this is the result of the expansion. Now you look at this formula, and you should see something strange. So who sees that there is something weird in this formula? It's a current, okay? There is a term that should not be there. So which one of the two is? Just on physical grounds. the minus 1. No, it's actually the other one. So the term that should not be there is this one. But why it should not be there? On physical grounds, no field theory, no mathematics, just on the basis of physics, simple physics. No, they are both real, and that is for sure. They're both real. Sorry? No, it's not that. It's not the fact that you have derivatives and constants and stuff. It's something much more basic. We have discussed it already physics-wise a couple of days ago. Much more basic. So let me ask, what are the electrons that should contribute to transport? Yeah, close to the Fermi energy, right? So which one of the two should be there and which one should not? Sorry? Which one should be there? So let's do this. 1, 2, oops, I should not write here. So you have 3 possibilities. 1, 2, I don't know. So which one do you choose? So which one should not be there on physical grounds because of what is said? Only electrons close to the Fermi energy are contributing to transport. The number 1, why? Because there is a Fermi energy. Derivative of a Fermi energy is something that is, close to the Fermi energy. The derivative of a Fermi function is a function that looks like this. It's centered close to the Fermi energy of a width that is temperature, right? This one is the Fermi energy. If this term was there, then this would mean that electrons all the way to the bottom of the band would contribute to your current. It doesn't make any sense. So how comes that this term is absent? And here you will understand why I wrote everything in terms of S matrices. Because you see, we forgot that we have to expand in gradients not only the expression for the current, but also the unitarity condition. And if you expand in gradients the unitarity condition, you get this plus that equal to 1. And therefore, this is gone. In the same order in the gradients, what is sitting here is nothing but the unitarity of the S matrix. So everything is consistent, physics-wise. And only electrons close to the Fermi energy are contributing to transport. Okay? And, believe me, this is something I understood that that should have been expanded on the basis of the reasoning, the physical reasoning I asked you to make. Okay? So this to say that sometimes to use physics is quite useful because instead of just using mathematics. All right. So at the end of the day, that's what we got. It's a rather simple expression, right? These are the instantaneous S matrices. You can just compute them with the instantaneous values of your parameters, and they're parametrically dependent on time, on the average time, and then you just have to take these 2 derivatives, and that's your current. Very simple. It's a very simple, very, very simple expression. And now comes the cake, which is what happens when I consider the charge that is pumped in one cycle. So in order to compute the charge that is pumped in one cycle, I have to calculate Right, so, well, first of all, let me rewrite the current I alpha. I can rewrite it as minus sum over beta integral d omega over 2 pi minus f prime of omega times the imaginary part of dt s alpha beta s dagger beta alpha. And now, okay, now you think in the following way. Let me assume that the time dependence is coming through a couple of parameters. Let me generically call them x1 and x2. So that's what I have. And along this cycle, let me integrate over this cycle over dt, and then compute the charge that is pumped in one cycle. Okay? Now, I'll make a long story short because, you know, you're all brilliant PhD students, correct? Correct about PhD, not about brilliant. You're all brilliant, but also PhD students. Right, so here you can, this thing here, you can write it as x dot dx 1 plus x2 dot dx2. And then you immediately see that when you compute this integral here, you can use Green's theorem, right? Because you're integrating and you have the line element sitting there. And if you use Green's theorem, you have minus beta, sum over beta, integral d omega. No, let me write it down here because I want you to see it well. So minus sum over beta, integral d omega over 4 pi, minus f prime of omega, and then you have integral over the area that is enclosed in by your cycle, dx1, dx2 over I, and then you have dx1 s alpha beta, dx2 s dagger beta alpha, minus dx2 s alpha beta, dx1 s dagger beta alpha. Now, this is a very non-trivial result, very non-trivial, because it tells you a couple of things. It tells you, first of all, that the charge that is pumped in one cycle in this adiabatic limit is a geometric quantity. It doesn't depend on how you move along the cycle, provided you satisfy the conditions of adiabaticity, but it depends only on what the cycle is and what is the area that is encircled by the cycle. These are the static S matrices depending on the parameters and x1 and x2. And you have to take these derivatives and take the difference and then take this integral. But in principle, this allows you to just compute the current. Not only that, the way we derived the current allows you to systematically study the corrections to the adiabatic limit, right? Because I can go to next order. I can go to the second order in the gradient expansion and see what are the corrections to this expression here. Since the corrections are going to depend on second derivatives with respect to time, I will not be able to use Green's theorem anymore, and therefore I'm not going to have a geometric result. It's going to depend explicitly on time, But I can do it systematically. It's not anymore zoology. That's what I wanted to say, because you have a limit in which you know perfectly well what is going on, which is the adiabatic limit. Right. And yeah, so now you can take this gradient expansion and you can apply it to your favorite problems. I mean, any problem in which you have convolutions and you have separation of scales, just you can look at it using the gradient expansion. Classical, quantum, no matter what. Yes. No, it does depend on the area. It doesn't. So I can move along this cycle in many ways, right? I can do this, or I can do many time dependencies, provided I always satisfy the conditions of adiabaticity. It doesn't depend on the charge. It does not depend on how you move. It depends only on what the circuit is. So it's geometric in this sense. It's a geometric quantity, right? So it's non-trivial. It's a very non-trivial result. And yeah, so. Well, so physically it could be, for example, that you have a resonant level and you have the difference between the couplings to the left and to the right, and you, I don't know, imagine doing, so you have your position of your level, well, let's do it like this, epsilon naught, and then you have delta gamma, which is gamma left minus gamma right, and then perhaps you want to do something like this. So you will first asymmetrically couple here, pull it down, then generalize the cycle that I mentioned yesterday, in which I was starting with the level that was pulled down. I was coupling it to the left. I was filling it up. Then I was disconnecting from everybody. I was pulling it up and coupling it to the right, and it was getting empty. So this is a path. This is one possible path. I'm saying you can take any path you want. For example, for a resonant level, you can choose this one and compute what is the charge that is pumped. But look, I mean, the story is, I'm sure that most probably you will not compute pumped charges ever in your life. But the probability that you will use the gradient expansion is close to 70%. Okay? So that's what you should keep in mind, not the pumped charge. So the gradient expansion is a very important tool in any field theoretical story. Right, so I have 15 minutes. So let me start. Well, I can cut it a bit short, right? Because we had half an hour more 2 lectures ago. But I wanted to tell you what I'm going to do next. So the thing that I'm going to do next is actually, I'm going to write down what is known as the kinetic equation. So you know what are kinetic equations. You have seen the master equations, Lindblad equations, the Boltzmann equation, any equation, whatever. And then comes the Keldysh kinetic equation, or Kadanoff-Baim kinetic equation. It has to be named after a few people because of symmetry between East and West, right? So, but it's which in principle contains all of them. But as you will see, it's very complicated. It's a very complicated equation. It's very nasty to solve it. It's not very easy. So what I'm going to do is I'm going to deal with a simple problem, as usual, which is the problem of fermions. So these are fermionic operators, subject to a random potential and to a smooth potential which varies in time and space. And I'm going to assume that the time scale of variation of my external potential are very, very slow as compared to Fermi wavelength and the inverse of Fermi energy. So it's a semi-classical situation, right? So in particular, I'm going to assume that KFL is much larger than 1, which means that the mean free path is much, much longer than the Fermi wavelength, and therefore you can think of electrons moving in this random potential. This guy is a random potential, as particles moving in a billiard, roughly speaking, as in the Drude approximation. And now what I'm going to do is I'm going to write the kinetic equation for this problem, and then I'm going to use the gradient expansion to simplify it as much as possible, together with another approximation that comes from the idea that, well, here it's pretty much justified. It's just free particles, but it could be justified also for interacting electrons. It's called the quasi-particle approximation. The quasi-particle approximation formally means that your green function is a simple pole. You assume that it's a simple pole up to renormalization. But what it means is that you can think of the elementary degrees of freedom of your theory as being quasi-particles. So I thought a lot about what is a quasi-particle. Well, a quasi-particle is something that has momentum and something else as good quantum numbers. It needs to have a momentum and a dispersion. For an experimentalist, a quasi-particle is a peak in a response function. So that's what they call a quasi-particle. So we will assume that your spectral density is highly peaked and around a certain dispersion, and then we will derive the Boltzmann equation. So from the kinetic equation, we will go to the Boltzmann equation. That's what we will do. And if time allows, then using the one last thing I want to show you is how to derive, using Keldysh, the Lindblad equation, which is another story that you probably know. I will do it for another simple system, but it's something that one can do in principle, right? All right, so any questions? Yeah. In this particular case, well, I think so. Okay. Let me tell you an anecdote. So when I gave this, so when I was working on this many years ago, I went to talk with David Towles. You know who is David Towles, right? And he asked me exactly the same question. So you're in a good position. He asked me exactly the same question. Right, so of course it will depend on this. So it's going to be important where is placed your contour, depending on whether these objects have singularities or not in certain positions in space. In this case, they turn out not to have anything special, right? But if you construct a problem or a situation in which you have some singularity and then your winding along this singularity gives you a certain quantization, then yeah, it is important on whether you go one way or another. Okay? So, same question is recurrent. Found it after 20 years. Other questions? Yeah, VR is a random potential. I will define it tomorrow, but it's a Gaussian disorder potential. So I will assume that it's disorder with zero average, and then delta correlated. It's a very standard way to describe disorder in fermionic systems in condensed matter physics. It doesn't really correspond to real life, right? Because in real life, if you take a piece of metal, you're not putting a random, a random Gaussian disorder. You're putting impurities, and the impurities are distributed according to a Poisson distribution, typically. I mean, unless you do something strange, which means that you pick some sub-block, and they are going to be distributed, with a certain average and certain variance, certain distribution, etc. Now, the thing is that when impurities are put in a material at very low densities, as compared to the typical time scale, length scales, etc., then the representation of the disorder in terms of a Gaussian potential is a good approximation. If you don't believe me, you're more than welcome to read the book by Schlossky. Well, I don't know how to write it. Schlossky and Efros. But believe me, it's not going to be a piece of cake. Okay, so it's going to be tough. So, but it's a good approximation, right? So I will use it. It's a good approximation for almost everything, and it's very much used in. Sorry? Oh no, it's a mistake. It's not. It's just a mistake. Other questions? Okay, so I'll see you tomorrow then. Well, I'll see you for dinner then.